Today I wanted to tell you about how animals and plants can inspire solutions for engineering challenges, and I wanted to use Terzaghi and Darwin as examples. We all know Carl Terzaghi. He's considered the father of soil mechanics. In my opinion, his most well-known work is his textbook on soil mechanics and engineering practice. And his most influential work is the theory of effective stress and consolidation. That has changed the way we do our practice. Charles Darwin was a biologist, and his most well-known work is The Origin of Species, and his most influential work is the theories of evolution and natural selection. Now, I checked, they didn't meet in real life, and that's because Carl Terzaghi was born 1 year after Darwin passed away. However, as I was putting these slides together, I kept wondering, if they looked at a picture like this, what might they be interested in? What questions might they ask? And so I imagine Terzaghi might ask, how do the roots of the palm trees provide it anchorage capacity, right? After all, the roots are all that are keeping these palm trees from tipping over. Whereas Darwin might have asked something like, how does the root system allow the palm trees to survive and reproduce? I think there's other questions they could have asked, for example, about the structural properties of the trunk, or the wind speed and hurricane power, that part is the loading, or why does the canopy take that shape, or what long-term effects might this storm have on those palm trees. And the reality is that we can ask questions like this about any given animal or plant that we see, from the amazing ways that an octopus moves to how snakes can climb trees, how insects can walk on water using surface tension, camouflage in fish to ambush prey, hummingbirds in flight and the amazing things they can do, to how mountain goats in certain trees can really cling on very steep surfaces. Getting more specific to the topic of this conference, geotechnical engineering, we build things that are analogous to what animals and plants do in nature. We build embankments, we build very dense environments, urban environments. We build tall and slender structures that are subjected to wind loads, excavate tunnels, install sensors, we build excavations. And if we actually take a step back, we can see that in nature there's dense environments, there's, I mentioned, the roots of the trees providing its foundation, snakes that move amazingly in shifting ground, and lions that use the angle of repose principle to hunt. Materials that are very efficient, clams that can bore in rock and wood, many examples that we can look at. So I think it's not about only admiring the beauty in nature. There are actually things that nature do amazingly that we could eventually learn from. For example, ants have been reported to be 2 to 3 times more energy efficient at excavating than our modern tunnel boring machines. Or the fact that root systems require about 10 times less material to mobilize the same capacity as a pile. To the fact that clams, earthworms, lizards, and many other animals can burrow without any reaction force, but we need to bring heavy equipment to do that. Snakes and lizards can move in loose and unstable ground, while this is still a challenge for space exploration. And finally, bacteria, roots, and fungi can stabilize cliffs and slopes, while we need to use concrete and steel to do so. So there are certainly things we can learn from this. And I think we have some challenges that we could use some help with. And so these are things that are already pressing us, and they will only press us more in the coming years. From the fact that the construction industry is using materials and fuel at rates that are not sustainable. We know that. Or the fact that we're depleting our sand resources, and that's a primary construction material. To the fact that the 10 most recent years have been the warmest on record, and that's bringing other issues like sea level rise, increased climate extremes, and thawing permafrost. We need new affordable and clean energy sources. The energy demand is only increasing, it's not going to go down. And also, the natural and anthropogenic hazards are only getting more complex and coupled and frequent as well. So in thinking about this, I was wondering what have been the ways in which we have solved big issues in the past. And so one way in ancient times was when civilizations met. There was always a trade in technology. When civilizations met, either peacefully or at war, there was an exchange in technology and in culture. I think one good example are the travels of Marco Polo and how when he went to Asia and he documented everything he learned, then he went back to Europe, and that helped a lot of the European civilizations advance their ways of life. Also metalworking and how that was developed in steps in different places around the world, but that allowed certain civilizations to create tools, to create jewelry and art and even weapons. And so then when civilizations met, then that technology propagated. Now, the reality is that as the world is becoming more globalized, the sources of new types of knowledge are disappearing. And I don't mean that we're not advancing knowledge, but in a way we are confined by what we already know. The sources of new ideas are harder to come by. So where can we look for new knowledge, creativity, and innovation? So we can look in outer space, we can look at the atomic level and get inspired that way. Maybe we can look for other civilizations, but as far as I know, we haven't done that yet. And so where could we look? And I think you already know where I'm going. Stephen Vogel was a biomechanics researcher from Duke University, and he was a big proponent of this idea, that nature provides an unlimited opportunity for innovation. And two of his quotes that I really like are that nature's technology represents the only known alternative to our own, right? And so when we're facing a challenge and we don't know how to solve it, we could look at nature for a fresh set of ideas. Or the fact that looking at nature, the science, it liberates us from the constraints of our own habits, history, and outlook. Looking at nature can help us take a step back, think outside the box, and look at our challenges with fresh eyes. And I think this is really shown by evolutionary trees like this one. This shows how life started from bacteria a long time ago, and then it evolved to other life forms, plants, fungi, fish, all the way to mammals. And what this shows is that as time went by, evolution created or resulted in different species. Now, a lot of those species didn't make it, and so you see a lot of those branches that dead end. Those are species that didn't survive. And the outer boundary of that ellipse are the species we have today. So we can actually see any species. We can see a dog or a goat or whatever you want, a fish, and look at it from the perspective of that animal or plant having a lot of strategies that allow it to cope with many challenges, and we can learn from that. So there's some differences between how engineering is done and how evolution works, and I wanted to point out some of them. First of all, in engineering, we have a goal. We have a problem, and we work to solve it, whereas in evolution, there really is no final goal. Evolution is driven by random mutations. However, the fact is that the end result is survival and reproduction. And so it's different from that point of view. So that allows you to think outside the box, not to be confined by your initial goal. Evolution works more as a tinkerer. And what do tinkerers do? Tinkerers just try a lot of different things without a real purpose, right? When I was in my PhD and my experiment wasn't working, I started tinkering. I started changing things until something worked. So tinkering is very slow. It takes a long time. But if you have enough time to try all the combinations, it's actually quite effective. And nature has done this for us. In evolution, trade-offs are the rule, and constraints are pervasive. From the fact that a given animal or plant only has a given set of resources and materials at its disposal, to the fact that they need to reproduce. And so, animals sometimes have these weird things like the feathers of a peacock, right? They do nothing to help it be faster or hunt, but it allows the peacock to find a mate. And finally, organisms must do a multitude of tasks, whereas in engineering, we typically focus on one or maybe a few. So there's a framework that I really like in translating biological strategies to engineering solutions. We can think of these as forms, which are physical structures. In other words, we can copy shapes and geometries and translate that to the engineering domain. We can go a little bit more abstract and look at behaviors. So movements, processes, and mechanisms. And the most abstract level is why the forms and behaviors are effective. Those are the principles. And so the more we go to the principles, the harder this translation is, but typically the more effective it is. And so that's a motivation to try to understand the underlying principles, because that allows us to be less affected by differences in the domains. So getting to the end of the presentation, I think right now we're facing challenges that Terzaghi never faced, or maybe Terzaghi never even imagined that we would be dealing with some of the challenges. You know, maybe he never thought we would be running out of sand. What are we going to do? I think that in his time, a lot of the projects were designed in isolation of their environment and even of the larger system. However, in biology and ecology, they've studied for a long time how a given change propagates to the larger system, how a given species going extinct affects the whole ecosystem. So I think there could be a cross-pollination here. Now, there's no question that the solutions that we have created in geotechnical engineering are safe and cost-effective. But I do think that if Terzaghi and Darwin had worked together, and here, again, Terzaghi and Darwin are an example. I really mean the communities. If we had cross-pollinated more, I think our philosophy of design would have been a little bit different. I think we would have emphasized energy and material efficiency, multifunctionality, and balance with nature. And so this would then help us to deal with some of the issues we have right now, developing sustainable, resilient, and equitable solutions. So to close this talk, Terzaghi and Darwin didn't get a chance to meet, but I think that we, as a community, can make sure that their legacies do meet to address some of our big challenges. Thank you.